Please go ahead.
Yes, okay. So what I wanted to do today is first kind of finish this set of slides that I could not finish yesterday, last time. So it's mostly I want to quickly finish this blue overview, then we'll go to the interesting graph decomposition things that I really want to talk about. And this will leave us time for, so in there's not really proofs, it's more like examples of how to use the technique. And then if you want, I can, I mean, if you're not tired and interested, then I'm very happy to show the proofs, but the proofs are not really in the slides. So let's also first do a quick recap of last time. Um, so we started here to define everything. So this was an example of a game to illustrate the notion of a strategy. Then we gave a real definition. So a strategy is just a graph with a morphism towards the game that satisfies a certain requirement in this diagram. And then we looked at a lot of examples. So this is an example where we can win, but strategies need to have memory for. Here's another example where the strategy needs countable memory state. Okay, this was an example of a parity game, and we discussed the fact that parity games have positional strategies, which are the same as strategies with memory 1, which is also the same as being a subgraph. Here's a mean payoff game, and finite mean payoff games have the same property that positional strategies are optimal. This was a maybe more weird example by boundedness, where we want to be bounded from both above and below. And what we saw is that in this example, we require like finite memory strategies are not enough to play in this example. However, locally finite memory strategies are enough in this case, and I claim they are always enough for this bi-boundedness objective as an intersection of two positional objectives. So there will be more details about how you can obtain such a result. Okay, then we looked at this example where I said that it's not easy to prove positionality, but it is positional. I think we won't go into the details of this unless you really want to. And we finished with this weird example, so where we have countably many colors, and we win if there's finitely many colors that have infinitely many occurrences. So that's maybe a bit twisted, and we'll come back to this at the end, just to illustrate how to approach such a question once we have our toolbox that I want to describe. Okay, then we went to this messy landscape slide. So here was a lot of blah blah. I think probably maybe a bit too much. I think I discussed most of it, but again, if you have some questions about some parts of this or some things that you would want me to describe on a high level, I'm happy to do this. So I think we discussed most of it. We did not really discuss these three structural results that are quite recent, but you know, let's I don't want to bore you with this state-of-the-art stuff. So I'll also go, and if we want to come back to this later on, then that's a possibility. And then this is the part, like, does not make so much sense, but this is the part where I would want to do research. So I think there's a lot of structural open questions, and this was a slide to talk about some questions that are open. So let me do this slide quickly, and then we'll go to the real, the tools. So this is the tool itself. The tool I want to discuss is So there's two variants of it, one variant that talks about positionality, one variant that talks about finite memory. The one from positionality was presented at LIX this year, and now we have a new paper which is on arXiv that extends this to finite memory, which is more general. And what it says is that if you ask questions about positionality, then it's the same as asking questions about some kind of graph decompositions. And another way to state it, and we will see how this relates, is by talking about universal graphs. So this is the same thing, graph decomposition in this case, and universal graphs. And the details is in the next part of the talk, and I'm going to then concentrate only on this. But first, I want to kind of put it in relation with the rest. So using this result, you can reobtain and re-understand quite easily in terms of graphs, because really what this result does is it takes this question about games and turns it into a question about graphs, and this makes it easier to approach when you talk about graphs only. That's the philosophy. And using this reduction to graph, you can re-understand some results from the literature. For instance, you can re-understand the result for topology closed objectives, which are easy to understand or in terms of memory. You can also have a new view on Mueller objectives. And also this arrow means that this tool is used in this paper, so a recent paper for that characterizes positionality for objectives which are recognized by deterministic Büchi objective. So they rely on this. So that's relationship with the recent literature. It's also a very recent result. And now I want to kind of discuss where I want to go with this. And so this is a slide from basically 3 weeks ago, but now I also have some new insights and questions that we can also discuss at the end. So first, one big research direction is about closure properties for classes of objectives which are, for instance, positional. And the main open question on closure property is whether positionality is preserved under unions. So this is only asked for objectives that are prefix independent, otherwise it's known to fail. But it's interesting when the object, so is it the case that two objectives which are prefix independent and positional, is it the case then that the union is positional? We don't know. We don't know, but we do know for finite games, then thanks to Sasha's work, that this is not true if you ask the same question for objectives that are positional over finite games. But for our case, so where positionality means positionality over arbitrary games, this is still an open question where I hope we can make progress. And then there's a variety of related, or not really related, but other open questions about closure properties. So this is a strengthening of this question, whether the union, whether the blow up of memory when you take a union is bigger than the product of the memory. So this is a stronger conjecture, right? This corresponds to memory 1. And this is also not known. So maybe if you want to disprove this, you can also try to disprove the more general one about memory. This is about lexicographic product. So I put it in blue because we can prove it that the memory of a lexicographic product. I will also explain what this is in the remainder. So it is the case, thanks to this tool, that the memory of a lexicographic product of objectives is smaller than the product of the memories. And it is also the case, thanks to this tool, that the memory of an intersection is locally finite if both have finite memory. I don't know if this holds if we just assume that both objectives have locally finite memory. So this is an open question about a closure property. Another question which was open until very recently, so that's why it's still written in green, but we solved it like 2 weeks ago, is whether this result is true for ordinal lexicographical product. But okay, whatever, that's maybe a niche kind of question. Yeah, okay, I'm talking too much already. So we can come back to this slide. It's about open questions. So I have some open questions, but it's probably not interesting to all of you. And I also have more open questions, so we can just have a discussion about open questions later on. And yeah, I don't want to already bore you with this kind of stuff. So I'll just move on if I think that's probably the better thing to do. So I'll move on to what I really want to speak about, and now everything was the introduction to this. So this is a new tool to approach positionality question, and I want to get going actually on an example. So our set of colors is, we have two colors, one safe color and one bad color, and we're playing a Kobushi game, okay? So we're looking at the objective where we win if we see only a finite amount of bad. So this is a very special case of a parity objective where we have just priority 0 and 1, and we win if 1 is seen only finitely many times. But now, as I said, we will not speak about games. We will really speak about graphs. Yeah? And to prove something on games, we will look for a property of graphs. Yeah? So that's what we're going to do. So we take a graph, which is possibly infinite, and we assume that the graph satisfies the objective. So what this means is that all the paths in the graph satisfy the objective. Yeah, so all the paths in the graph have finitely many occurrences of the color bad. So these are colors on edges, and we have a graph where on each infinite path there's only finitely many bad. And then the question is, well, under this assumption on the paths of the graph, can we say something about the structure of the graph? Yeah. That's really going to be always the same question. Well, the objective will vary, but that's the question that matters. And now if you think about it for a while, under the assumption that all the paths have finitely many bads, you can figure out that the graph has a kind of a layered decomposition where each layer corresponds to, from a given vertex, what's the worst possible number of bad that I can see from a given vertex. So since the graph is possibly infinite, there are possibly infinitely many layers, and the layers actually corresponds to ordinals that capture this worst number of bads. So this is something that you need to wrap your head around, but you get this kind of layer decomposition where all the bad edges have to go down strictly, because if you see a bad, then in the future you will see fewer bads. And the safe edges, they can either go down strictly or stay in the same position. Yeah. So again, any graph, even possibly infinite, that satisfies a Kobushi objective like this has a layered decomposition where the layers are indexed by ordinals, and where all the bad edges have to decrease in the layers, and the safe edges can either decrease strictly or stay in the same layer. And really, once you understand this, well, you've understood graphs satisfying Kobushi. This is exactly what such a graph looks like, and every such graph satisfies Kobushi. Okay, so there's no longer any mystery about graphs satisfying Kobushi. We've understood them. So that's the graph decomposition I was talking about. And now I said that this is equivalent to something about universal graphs. So let me say it on this example.
Sorry, Pierre, what's the
Yes.
problem if we go up with the green edge
With
to a larger,
a safe edge?
by safe edge,
Yeah,
but to a larger?
then you might create a cycle where you do safe, bad, safe, bad, safe, bad, and
Ah, see, yeah, yeah.
So the point is, if I see this
So
is
the
why
claim is that the graph has this property if and only if it can be classified with this layers.
exactly.
Yeah.
And now I'm just going to rephrase this in terms of universal graph. So let me introduce a graph. So it's a graph here defined over all the ordinals. Okay, so this may seem a bit dangerous, but let me still do it. So I have a graph where the vertices are all the ordinals, and the bad edges, they follow strict decrease. Yeah, so whenever I go from something greater than something, there is a bad edge. Yeah. And the safe edges, they follow non-strict decrease. So I have safe edges going strictly down, but also staying in the same place. Yeah. And this is my graph. Now let's look at this graph. So first, it holds that the graph satisfies the objective. So this means any infinite path in the graph has only finitely many bads, right? This is because whenever I see a bad, I'm forced to decrease strictly, and whenever I see a safe, I will not increase again, so I would always decrease. And now I have a path that corresponds to a decreasing sequence of ordinals, then it can only have finitely many gems, right? So there's only finitely many bads that can occur, right? Is it clear what this means, and is it clear that it's true?
So the only claim is that you cannot have the infinite path in this graph, or you claim something else.
Now I'm claiming that any infinite path on this graph has only finitely many red edges.
Yeah.
Yeah. This is what's written here, that the graph satisfies the objective. Second, I claim that if I have a graph G that satisfies the objective, then it embeds into U with a graph morphism. And this is what I said. This is just a rephrasing of what I said on the left. It says exactly that any graph G that satisfies the objective can be partitioned into layers such that the edges are in this way. The bad edges have to decrease strictly, and the safe edges have to decrease but non-strictly. This second statement is equivalent to what we said before, that graphs satisfying the Corbusier objective have a layered decomposition.
So what are the requirements for this mapping of G to U?
It's a morphism, so it preserves the edges. So any edge in G is also an edge in U. So this means that the edges in G the bad edges have to decrease strictly.
So how do we do this? Imagine we have a graph with some G is mapped to U. Yeah. Sorry.
Okay, so these two things exactly somehow restate what we said before. Yeah. It's like a compact way of saying this property. And this is what we call a W universal graph. Okay, so it's a graph that satisfies the objective and that embeds all the graphs satisfying the objective. Okay. Now I'm being a bit like high level here because I'm allowing myself to define a graph over all the ordinals, which is not really a set, so it's a bit dangerous. So the way you would overcome this difficulty is to look at being universal for some fixed cardinality. So you would fix a cardinality kappa and ask that your graph U embeds all graphs of cardinality smaller than kappa. Okay, but at this point I want to remain a bit maybe hand-wavy and just say that this graph defined over all the ordinals is universal. Okay, so it's universal, but it has additional properties. Well, it's well-founded, right? It's defined over ordinals, and it's monotone. So monotonicity is a property of the graph U plus the order. So here the order is the natural order over ordinals. And monotonicity tells you that if you have an edge in your graph with color C from V to V prime, and if you actually start from a higher point and actually go down to a lower point, then you still have an edge. So it means like Yeah, usually I would do this on the board, but now I can't really use both hands. I have just one cursor, but it means that if I have an edge, I can stretch it. Yeah, so a bad edge, I can take the head and push it down, and I can take the tail of the edge and pull it up, and then this would still be an edge. Yeah, you can stretch the edges along the order. It's always push down the head and pull up the tail of the edge. Yeah. This is what I call monotonicity. Another way to see it means that yeah, no, yeah. So this is monotonicity.
Okay, but we are trying to prove something now. So what is happening? So we try to give a definition or to prove something or what?
So I'm proving that for the Kobyshi objective W,
Yeah.
there is a universal graph which is well-founded and monotone.
Sasha,
No, but-
and
but
the
in-
idea is that if you have these things, then this implies you that you're oppositional. If you have a universal graph which is well-founded and monotone.
Oh, but
So
the
just
definition of the
little-
universal graph, does it include some order or not?
No, but monotonicity does, and well-foundedness and monotone is of course with respect to the same order.
Yeah, okay.
There is always a universal graph, which is the union of all the graphs that satisfy the objective. Yeah, disjoint union. But this doesn't have any structure, so it tells you nothing. But if you have an additional structure, which is a total order, which has to be well-founded, and moreover the graph is monotone, then this characterizes positionality. That's the result. So that's the result that's going to appear here. Yeah. And this I want to maybe prove it today. So that's the main result I want to talk about. Okay, so
V is just a class of infinite string.
Yes.
And then what is the general definition of monotone V universal graph?
So this
So
is
just
monotone.
say it again.
Yes. So universal means I satisfy the objective and I embed all the graphs satisfying the objective. And it's the same as saying that the graphs satisfying the objective have a kind of a graph decomposition in two layers. I mean, having a universal totally ordered graph is the same as saying that all the graphs satisfying the objective have a layered decomposition. And then if you assume that moreover your universal graph is well-founded.
But just V is just a class of strings, of infinite strings, yeah?
Yes.
And so we don't have any graph. So we just start with some class of strings.
Yes.
And so then we consider some graph U, which is labeled by this by the same alphabet.
Yes.
Yeah. And also we have some order or additional
on the vertices of U. Yeah.
Sasha, we do not have any order on our graph G. So the claim is that
on U we have the order.
On U, but not on W.
No, W is not just a graph. W is just a property of infinite strings, yeah?
Yes, and we want to give some characterization of the following property of W. That for any graph.
For any graph, the game has a positional strategy.
With objective W.
With objective W, that's a positional strategy.
Yeah.
And the claim is that there exists some graph U and some ordering, yeah?
Right.
So say it again. What is the property of this graph and ordering?
But U is universal first, and U is monotone and well-founded.
So universality is just a property without order,
Yes.
which doesn't mention ordering.
Yes.
Right.
And what is the connection between graph and ordering?
The monotonicity.
And also when well found this.
Yes.
Well found.
So the monotonicity, it means that the arrows go down, or what?
It means that it's kind of like a downwards closure. It means that if you have an arrow, then you can
Stretch it.
If you have
Stretch
an
it
arrow to
down.
somewhere, you also have arrow to places that are before it. And you so this means you can push down the head of the arrows, and you can also pull up the tail of the arrows. Yeah, it's this
But we don't require that arrows go down or what?
No, this is not required.
No, that was required only in our example. So for our example, universality requires going down. But in general, we do not require it.
Yes, thank you.
And we just require such a strange...
It's not so. So what it means essentially is that if you look at your, so the vertices are given by well order, right? So they are essentially ordinals. And then each color gives you a relation between ordinals. And and what you say is, well, if you look at this left part, what you say is that if I fix V prime and I fix C, then the set of predecessors is upward closed.
Yeah.
So this says that, and now I'm on ordinals. So I have an upward closed set of ordinals, so it has a minimum. So what you're saying here with the left part is that every V prime and C, there's a minimal predecessor. Yeah.
Yeah.
And this completely, if you have the data of the minimal predecessor of each V prime, then this completely tells you where the edges are. Yeah. And now this other thing on the right tells you that this map, so if you fix C and you look at the map which maps V prime to its minimal C predecessor, this tells you that this map is increasing, or is how do you say, monotone. So essentially this means that each of the color relation is monotone.
So what is somehow confusing for me, just in our example, there was quite clear in this W, there was clear why we get some well ordering, because paths are all paths are finite, and just for arbitrary W, there is no intrinsic well ordering on anything. It just
but I will show that such a graph, assuming positionality of W, such a graph has to exist. That's the main novelty. That's the main result.
Okay. And so the first cut, so there is some more or less unique universal graph for a given W, or there could be quite different, but they are.
So this is a discussion for later.
Okay.
Okay, but let me. So I have another. So this is a simple example. I have another one. But I think the statement is clear at this point. So I'll go on to a second example, which is Bushi. Okay, just to this is another simple example which is well known to be positional. So I have two colors, good and weight, and I win if I see infinitely many goods. Yeah, so I don't want to get to a point where I will wait forever. Okay. And then we ask the same question about decomposing graph. So is it the case that we have a graph, possibly infinite, we assume that it satisfies the objective, all the paths have infinitely many goods, and then we ask again, what's the structure? Yeah. So can you come up with, so I claim that it has, whoops, I spoiled it maybe. So I claim that it has a layered decomposition. Can you give support to this claim? Do you see it?
So just a complement, right? Or I'm missing something.
A complement? Ah, yeah, this
So
is
the
just
property is a
the complement
complement
of
of.
Cauchy. Yes, exactly, yeah. And renaming the colors, yeah.
So you want to, like, you want to have some ordinals. Well, you want to have ordinals and you want to draw edges between them some way that you can have, that you cannot have infinitely many, oh no, that you cannot have only W's.
Yeah,
Starting from
like this,
some
yeah.
mono.
So I mean, I think at this point it's simpler to just say I want to understand the structure of the graphs that satisfy a Buchy objective, yeah. And then how do they look like? And the answer I'm looking for is something like a layered partition. Yeah.
Okay, does anyone understand what is this, what is the answer? I have no. It's for me it's strange. You how.
I don't see how the layers should look like. No.
The point is, yes.
So we need some. We need some order. Some graph on ordinals.
No,
Yeah?
forget about the ordinals. We want to find some decomposition of the graph, ensuring that property. So how can it happen that every path has infinitely many goods?
Yes.
Well,
So
probably all
yes.
W's should go down, right?
Uh-huh.
So that, and then G's can go in any directions.
Yes,
In any
great.
direction.
Great. So that's it, yeah. So let me explain. So again, I'm gonna have a layered decomposition, and you need to understand, you need to count something basically. This is what it means, having this layered decomposition. And what we count in this case is, well, from a given vertex, how we know that we will wait only a finite number of time until the next good, right? And now the question is, how long am I going to wait? Okay, so before it was how many bads I am going to see in total, and now it's how long do I have to wait before the next good is ensured. Okay, so this is what the layers capture intuitively.
And it's again an ordinal number.
And it's again an ordinal number because the graph is infinite, so yeah. And now if you want to understand where the edges are, well, whenever you see a weight, then you will weight less. So you go to strictly better layer. And whenever you see, well, the goods can be actually anywhere. So for instance, if you are in the layer number 0, you have only one option, is to see a good edge. You cannot weight more from there. You know that you are done with the weighting. You can only go up. Yeah. But actually, since we're looking at the worst case, there can be good anywhere. So that's the decomposition. Weight go down, and good can do anything.
Yeah. So and now you want to say that this is somehow corresponds to some universal.
Yes. So here's the graph. So the bad edges go down, and the good edges are everywhere. Now I should check that these
I
graphs.
think I think that the main result can be expressed without any reference of the universal graph.
Yes, that's
So
that's
you
also true.
mentioned that actually positionality means some kind of decomposition.
Yes.
Is equivalent to some kind of decomposition.
So it means decomposition into into an ordinal, like layers indexed by ordinals, with a monotonicity property on the requirement for edges. So basically, I think it's just more convenient to say it in terms of universal graphs, but it's true that this object of a universal graph need not really be defined. I don't know if this is a satisfying answer.
So let's say that a mapping into the universal graph is
Yes.
just a labeling by ordinals, because elements of universal graph are ordinals.
Yes.
And so what do you require about this labeling? Can you say again? So
we require that there are like the decomposition has some monotone rules. Like here the rule would be weight edges have to go down and good edges can be anywhere. And this rule, I say that it's monotone because it has this stretchability property, right? Whatever is stated by the rule can be stretched along the order. That's the monotonicity property.
yeah, but in general, imagine we have arbitrary W.
Yes.
And then we say that a graph satisfies the W property. So all paths have this W property, if and only if we can label each, if we can introduce an ordering on ordinals, yeah, and a mapping on a graph into a labeling by ordinals.
So the ordering on ordinals is always going to be the natural ordering. There is no there is no extra ordering on the ordinals.
Yeah, of course. Oh, yeah. But there is some we just label our vertices of our graph by ordinals.
Yes.
And then we require something. And so just what is this requirement?
So the requirement depends not on the graph but only on the condition, and it's specified as for each color a monotone relation on ordinals. And this is exactly the same thing as a universal graph. No, and plus this monotone relation should also satisfy the objective. So I mean,
maybe, sorry.
Yeah.
Maybe the confusion is if you have just a graph which satisfies W, and then you introduce some layer decomposition. Then there are some edges. But if you have an arbitrary graph, they might not be monotone, right? So you might not have all edges.
It's arbitrary graph. We don't have any edges.
The claim is that if the objective W is positional, then you will be able to come up with such a decomposition.
But then if you just have a decomposition, then you have to kind of close. Consider a closure.
That's also that's a good point. That's another way to state the monotonicity thing, is that so a condition is positional if and only if any graph satisfying the condition has a layered partition such that I can close the edges under the order. So I would add more edges. Like for instance, in this example, do you see my cursor?
Yeah.
For instance, in this example, I don't know, I have a good here. Now, let's take this good here, okay? And now I want to say that I fix this partition, and I want to close the graph with respect to the order. So I would add this edge here would produce many other edges that go to anything which is in a lower layer. And the claim
Yeah, and
is
the
that
graph should
by
be still
adding all these
satisfy
edges,
only
I
graph.
should still satisfy the objective. Yeah, so that's maybe that's a good universal graphless statement, saying any graph has a layered decomposition into ordinals where the layers are well founded, and such that I can close with respect to this decomposition, so add a number of edges and still satisfy the objective.
Yeah, so every path which goes along the edges and also has some kind of arbitrary jumps in order in decreasing direction
Exactly.
satisfies W.
Exactly. So it's a kind of well-ordering principle that you can well-order any graph with this strong property that you maintain the property that you satisfy the objective. And this is if and only if the objective is positional.
And can you show, please, the previous slide?
Yes. Like the Kobushi?
Not this one. A definition of the universality of a graph.
Yes.
I mean the previous one.
Yes.
Aha, this one. Thanks.
So actually, I'm moving because it's the definition is again repeated here. So let's have it here. Yeah. So here again, let's just check the two things. So the graph satisfies the objective. This means that every infinite path in the graph has infinitely many goods because you cannot wait forever. All right.
Yeah.
And then this second item says what I said about the layered decomposition. Any graph satisfying a Bucci objective has this layered decomposition, which is the same as a morphism into U.
Okay, so it's sounds very interesting and strange. So, but just let me ask the following question. So,
yes.
For example, we have this property for I don't know, parity games. We have this W parity property, and so now you say that there are two. We want to prove the positionality, and then you say that there are two steps somehow. First, we need to see that this property has this universal graph, and second, you need to show that if the universal graph exists, then the game is positional.
No, this is true in general, that if you have such a universal graph, then it's positional.
Yeah. So now we split the proof of positionality for parity games into two steps. And so where the main problem is somehow, or both steps, now with this new definition, both steps are simple,
So given now, if you take an objective and you want to prove that it's positional, then it suffices and it's necessary to find a construction of a universal graph. So it's kind of methodological progress that now we have a tool and we know that it always works.
Okay,
so
but if we apply our tool for parity games,
yes.
So what is the difficult part and what is easier part in these two parts?
So the two parts that you talk about is first coming up with a graph and then
having this
right to left implication.
Yeah, right to left implication. Yeah.
I don't know. I mean, the implication is not so hard. I mean, it's I don't know. Good question. I think the hard part is still coming up with a universal graph. But since we know that both implication holds, then we know that it's all about finding the structure. And conceptually, it's much. I think it's simpler. It gives a good angle to approach the question, but it's not.
No, just. But if you take somehow imagine you combine these two parts for parity games, you get some kind of a new proof for.
So you get Emerson and Jutla proof. So you can look at the proof of Emerson and Jutla, the first one.
Yeah.
And you can look at it once you know the definition of a universal graph.
Yeah.
And immediately you will see that what they are proving is,
it follows
what they are
the
giving is a construction
yeah.
of a universal graph. Even though they do kind of, like they do some, instead of just chaining the two implications, they do not really talk about graphs. They have some factorization where they directly prove something about games. But you can take their proof about games, look at it for graphs, and then this is a proof of universality. You can essentially break it into two parts.
Yeah, and so you say that and if you argue about parity games, for example,
Yes.
and somehow the statement doesn't involve any ordinals at all. But you are saying that they appear somehow in natural way.
Yes, if you look at their proof, they have these tuples of ordinals, and this is the universal graph. This is signatures. I don't know if you've seen signatures.
No.
It's the same as if you've looked at progress measure algorithms for parity games. It's always the same concept that you somehow count the number of odd occurrences before the next bigger occurrence, and this defines a universal graph, basically.
Okay.
There's just one proof, yeah.
Maybe it's time to see the universal graph for parity games.
So it will come in a little while, and actually I think it's better presented as it's an instance of something more general, which is a lexicographical product. So, but it will come. So you okay. So the way I wanted to proceed now is to show how this extends to memory. But already here for positional, it's an interesting result that have some consequences that I don't yet understand. So we can just discuss also positional. But the way the slide is done is that now we extend to finite memory. So let me just show you how you adapt it.
Yeah, that's exactly why it would be better without slides. But okay, because you are following some specific path. But okay. If it's you are prepared to this, let's do this.
I'm sorry. I think my connection broke.
No. I just wanted to say that why it would be better without slides, because you just have to move along the line.
Yeah,
and you cannot go in completely different direction. But okay, let's do it like this.
But it's not so bad. Yeah, sorry. No, while you were speaking, my connection broke. So I hope this does not happen again. And if it does,
okay. Sorry.
Okay. So the way it extends is if you don't care about positional but finite memory, then the order on the universal graph is no longer a total order, but it's a partial order. So the graph has some kind of width. And by width, I mean the size of the antichains in this partial order. And it needs to be a well-founded partial order. Yeah, and then this result works. So if you want to understand objectives that have memory M, so some finite M, then it corresponds to having a universal structure which is partially ordered and such that the antichains are bounded by M, and it's well-founded. Okay, so that's the extension, and I can also give details to this. So it's on archive also. And here's an example actually of the finite memory case. So let's say, so this is a Mueller objective. So we have two colors A and B, and we win if both occur infinitely often. Okay. And this clearly, this is not positional, because if you have to make all the choices, then you should make some different choices. You cannot play positionally in this game. But it's memory 2, okay? And now I want to show how to obtain this memory 2 result with a universal structure. So again, it's the same kind of proof concept. Start with a graph and look for, assume that the graph satisfies the objective. So all the paths have infinitely many A's and infinitely many B's. And then we ask what's the structure. And now we get a kind of a double layer decomposition. So you have to think for a while. And this gives you not a total order, but it gives you a partial order with width 2, which is here drawn as a universal graph. So you have these two components, and in the first component, A decreases strictly, but B goes to the second component. And in the second component, B decreases strictly, and A goes back to the first. And this graph satisfies the objective. If I take an infinite path, well, I will wait with A, but I cannot wait forever. At some point, I have to see a B. And then again, I cannot see B's forever. I will have to see an A in the future. So this does satisfy the objective, and actually characterizes the graphs that satisfies the objective in terms of having a morphism. Yeah.
Sorry, Pierre, when you go from one part to the other, you save you stay on the same
No,
level,
you
or you can
reset.
go
You go. Otherwise, there would be no or not many infinite
infinite
paths.
path.
Yeah, or there would be maybe this path, but that's too
Yeah.
restricted.
So, and
Then
I
you
also
reset.
have a question. So imagine you have a graph where, so I mean, where you have the nodes are pairs of ordinals, right?
Mhm.
And when you go by
Yeah,
A,
yes,
you should,
so there's a lie on this slide, and it's going to activate right now. But maybe you found the lie, is that this is not true. um, but it's almost true. So I think this is what you wanted to give a counterexample to,
yeah,
Sasha?
I mean,
Yeah. So I
so
lied. But it's gonna be fine in the end. So, but still, so this is not true, as Sasha already pointed out. I wasn't
okay,
expecting
so that's not true.
someone
That
so
this
bright.
graph that you drawn is not universal.
It's not universal, but almost. So, but and the point is, it's universal in the sense that it embeds all the trees. And this
Yeah,
is the notion of universal. So in the case of well-founded graph, it's equivalent to embed all the trees and all the graphs. But if you're not, well, if the order is not total, if it's a partial order, then it's not equivalent. And the good notion is embedding all the trees.
but in your theorem, the requirements for trees
Yes,
in the result.
yes. And in the case of positionality, it does not make a difference, because if you take a graph, then you can unfold it. You have a tree, you embed the tree, and this also gives you an embedding of the graph, actually, because of well-foundedness. You can fold it again somehow. This is what the proof does. So for positionality, it does not make a difference. Here it does make a difference, and the good notion is embedded trees. So U is a graph, and it's important that it's a graph and not a tree, because we want to have bounded width, but we just need to embed the trees. I think this is more like, yeah. I mean, we can just talk about positionality. It's enough content, I think. But this is how it extends. So you consider being universal for trees, and you look at the width of the order. Okay, and then here was another example, but then I realized that actually my construction is wrong. So let's, I don't want to say wrong stuff, so let's forget about it.
Yeah, but
okay.
just before, so,
Yes.
so you say that W is positional.
Yes.
It means that if there is a winning strategy, it's
Yes.
positional, but it doesn't say
No,
anything.
it said if there is a winning strategy, there is a
Positional winning
Yes,
strategy.
yes, yes, yes. So this is property of games, and on the left, and on the right, it's a property of graphs. That's what we've gained. It's maybe a weird property, but it only mentions graphs.
Okay, but if we just have no requirement on memory and just allow whatever we want, then the left-hand side is trivially true. Yeah.
Yeah. Okay.
So something you say that for every W, there exists something without any
Yes, that's because you can always take
what is this?
take a union, disjoint union of all the graphs that satisfy the objective. This is universal in the sense that it satisfies the objective. All the paths in there are paths in some.
But how do we get this ordering?
Yeah, so the point is well, if you take as a partial order the empty partial order, you have no order, then it is monotone because monotonicity says nothing in this case.
Yeah.
So any graph is monotone of width, its size. Yeah. But then the point is you want to add structure. You want to shrink the width of the universal graph. So this is another way of seeing it. You can start with this huge graph, which is the disjoint union of all the graphs satisfying the objective. If you're unhappy with this, you can also fix a cardinal upper bound and then work with graphs smaller than this cardinal. So you have this huge graph, and it's all about adding structure to this graph to like shrink its width while still preserving satisfying the objective.
Okay, but so okay. So what I'm so strange for me. So for example, imagine we have some W and for example we want we have some graph and we want to find is there a winning strategy or not in a given graph.
Yeah.
So imagine we in terms of this universal monotone things for W, the existence of a winning strategy means what?
So now you're talking about the decision problem, or
no? Yeah, no, it's not a finite problem. So I just want to maybe so we have some graph, and we have some property W, and the properties analyzed according to this. For example, it's positional. So there exists some monotone and well-founded universal graph, linearly ordered. And then we want to find whether some graph, for some graph, there is a winning strategy.
Yes, even for a game, you can.
Yeah. So how do we?
So you can compute the smallest. This is called the progress measure sometimes, and do you know progress measures?
No.
Okay, so I can explain. It's
no. Maybe then it's better. No, I don't know. Let's continue. Maybe Sasha understands and then later explains it. Okay, don't worry.
No, it's just a few words. So
okay,
if you have a graph. You have a specific graph, let's say for now a graph, and then I will explain that it also works for a game.
Yeah.
Okay? But let's say we're looking at a graph, which is the same as saying we have a game which is only controlled by the opponent.
Yeah.
Okay? Then we ask, is it the case or not that this graph satisfies the objective? So all the paths satisfy the objective, which is the same as saying I win the game even though it is controlled by the opponent, right? Okay, and now we also have on the other side a universal graph, totally ordered, okay? And we want to use it to devise an algorithm to answer the question whether the graph we start with satisfies the objective or not, yeah? And what we can do is there is a notion of the smallest, like pointwise smallest morphism. And there is an algorithm to find it, which is a very simple greedy algorithm, which is first start with the mapping that maps everything to the very smallest point in the universal graph and see if this is a correct mapping. So does it preserve all edges? If it doesn't, it means that one of the edges is not preserved. Then pick this edge and take in this graph the source of the edge and augment it until, and since you have a monotonicity property in the universal graph, there is a well-defined point at which you can augment the vertex so that now the edge belongs to the graph. And just by running this greedy algorithm, you end up either finding a morphism or never terminating somehow. And this way you can also answer the, and this is called the value iteration algorithm. So universal graphs, they give you the structural result, like this is positional if you have the totally ordered universal graph. But in this case, they also give you an algorithm.
Yeah, okay. I'll later ask Sasha, maybe.
Okay.
And that's all strange to me, but just continue.
Okay. So what I wanted to do next is to talk really quickly about these lexicographical products. But again, I will be quick here because I think it's a bit non-essential, but it gives you one application of the result. So here's the picture. Let's say we have red-orange graph, yeah, with several reddish colors, and this is a graph with also a partial order. Yeah, that's the kind of object that we're looking at, graphs with partial orders. Let's say we have two of these. Then there's a natural way of combining them lexicographically. So each vertex in the there's also importance of the colors. So here the blue thing is more important than the red thing in this example. Yeah, so the one on the right is considered to be stronger. And then there's a way to combine these lexicographically by like replacing each vertex in the strong one by a copy of the weak one, and then like globally preserving the structure of the strong one and locally the structure of the weak one. And the point in doing this is that then you can prove a theorem that if the first graph is universal for some objective over the orange colors, and the second graph is universal for another objective against the other stronger blue colors, then their combination is universal for the lexicographical product of the two objectives. And this I did not yet explain what it is, and unfortunately I think I don't have it on the slide, but let's explain orally what is this. So is the statement clear? I mean, I need to explain what this is, this lexicographical product of the two objectives, but I already explained using the picture what is the lexicographical product of two ordered graphs. Yeah, and then this is the theorem. Right? Is the statement okay?
But then you also should say,
I need to explain this, what's in the parentheses.
yeah, and you also want to maybe, as I understand, if you want to apply it for games, then you also say that this lexicographic product of graphs is also, if it's one is well-founded, the other is well-founded.
Yes, exactly.
Then you just say it's monotone and well-founded with respect to the lexicographic orders.
Yes, so this is also
device.
this is an ordered graph, and it is like the partial ordered here is the lexicographical product of the two partial ordered here and here, and if the antichains in there are bounded by the product of the antichains. So this is what comes after. So this theorem implies that the memory of the lexicographical product is bounded by the product of the memory, thanks to as a consequence of this. Yeah. And now I just need to explain what all of this is about, right? So the lexicographical so I have two objectives, W1, W2. that are defined over disjoint set of colors. That's really important. The sets of colors are disjoint. And I see the blue colors as being stronger than the red colors. And the product is, I accept a word. Well, look at the word. There are two cases. If there's infinitely many strong colors, then I take the projection on the strong colors and I look if it belongs to the strong objective. And otherwise, if there are only finitely many strong colors, I look at the projection on the weak colors and I look if it belongs to the weak objectives. And I assume that everything is prefix independent for it to make sense here. Okay, so I'm only talking about prefix independent objectives. So Sasha, did
So
that?
let's say parity games
Exactly.
like that.
Yes, exactly. So that's one application. So this way you can get positionality of parity games just using positionality, for instance, of Bucci game. You can even do it using positionality of very trivial conditions. Like you have a condition over a unary alphabet which is winning, and a condition over a unary alphabet which is losing, and then parity is a product of these very trivial conditions. So for these conditions, it's completely trivial to see positionality, and then you get positionality of parity games using the theorem. So that's, I mean, it requires some tools, but then I think it's a super simple proof for parity games. But you know, it's a bit maybe like it requires some tools. But yeah, this is a general result, and it's also true even if the lexicographic product is not finite, but this requires some more definitions. Maybe I can expand on this later. If
Just for parity games, it means that all the difficulty, well, in this theorem and in one direction of your uh, general characterization.
Yeah, you can see it like this. I mean, at this point, this theorem is also has some difficulty inside it. I mean, we're kind of doing reverse math, hand wavy reverse math. I don't know if it has I mean, it's hard to, but yeah, something like this. So then the question is, so this is very successful for lexicographical product, but it's also not surprising because, like, if you take product of ordinal, it's a lexicographic product. So it's very natural in this sense that lexicographic products work well. But then a question is, can you have a similar construction that works well for union? Yeah, so that's one question that I don't know the answer to. And now this slide is going to be maybe more entertaining. So it's back to this weird condition, and what I want to show here. So I don't know if you had a thought on this condition since last week. So it's I claim that this is difficult to approach, and now I want to show that using the tools we can approach it with reasonable difficulty. So it's kind of an illustration of. So in this example we've used mainly the right to left direction. That if I can come up with a construction, then I obtain positionality. And now we're kind of going to use the other direction in context. So we have countably many colors, and we win if there's only finitely colors that appear infinitely often. And the question is it positional or not? And let's say we don't know. I mean, it's hard to have an opinion on this, I think. So does anyone have an opinion whether it's positional or not?
Yeah, I mean, it's strange that you're saying that we'll use it in the other direction. So then it's not positional or what?
Yeah, maybe. So that's a reasonable guess. But I mean, have you looked at it? So I think if you look at it, it's not easy to have an opinion on this question. So let's try to prove it's positional, but you might have guessed correctly. So if we want to prove that it's positional, then we should be able to come up with a universal graph. Yeah, that's the methodology. So let's see. Well, first, so let's see how you look for a universal graph. So, well, my universal graph definitely, so this graph here, just the loop, it satisfies the objective. There is only, so on each path on this graph, there's only finitely many numbers that appear infinitely often because there's only one path and it has 0, and there's only 0 as the only number that appears infinitely often. So this graph satisfies the objective. Okay, so it should appear in my universal graph, right? So let's start there. Likewise, this graph, I have two loops, 0 and 1. And now the paths, well, they have some occurrences of 0, some occurrences of 1. But again, there are still only finitely many numbers that can appear infinitely often because this is just 0 or 1. This is most size 2, right? So this should also appear in my universal graph. And now we want to make the graph monotone. So we should order these two somehow. We should say that one is bigger than the other. And if you are a bit used to working with this, it makes more sense to have this one bigger. So let's take this one to be bigger, yeah, and see if we can go from there. And now, so since I take this one to be bigger, I need to have this stretchability property. So these loops, I need to also have them go down there. Yeah, this kind of downwards closed thing. So I need to have 0 and 1 going down, but I can actually put anything, right? I would still not break the objective because this one I use it only once. Yeah. So this graph still satisfies the objective, and it needs to appear somewhere in my universal graph, right? So it's there somewhere. So let's put it. And so on. This graph needs to appear, and actually this graph here. So is it clear what the graph is? I have all the loops, 0, 0, 1, 0, 1, 2, and so on, and all the edges pointing down. Yeah. So if you think for 5 minutes, you come up with this candidate. I think that's the one reasonable first candidate for being monotone universal graph. Right? Is it okay so far? So this graph satisfies the objective because if I take a path, an infinite path in there, well, it has to at some point loop somewhere. And then once it loops, well, the occurrences are only bounded within a certain set. So
also we have paths where all natural numbers appear, but only finitely just 1, 2, 3, 4, 5, and so on.
No, you don't have this path. That's the whole point because you don't.
What is the condition then? Say it again.
So the condition is that so you take a so you win.
I thought that there are only finitely many numbers that appear infinitely often, or it's different condition.
No, it's this condition.
But so if you take 1, 2, 3, 4, 5, 6, 7,
yes,
and so on,
it belongs to the condition.
Yeah.
But actually not to the graph.
Yeah, but is the graph universal then?
So it's not. So you took a bit small shortcut and came up with this, but yeah. So let's go there. So here's a graph that. So you think this is my candidate, and you wonder whether it's universal or not. And okay, I had some additional blah blah to answer the question, but you answered it. It's not universal because of this graph. This graph here satisfies the objective, but does not embed into my universal graph. Okay, so now we have a graph that seems to be a bit hard to embed somehow because our first candidate does not embed it. And you could pause at this stage and start to think that something's going wrong because you have this graph here, 0, 1, 2, blah, blah, blah. And you need to make it monotone, right? It has to embed in the universal graph. So you should be able to put a well-founded order on this and close with respect to this order, right? But there's only one well-founded order you can put here, which is 0 less than 1, I mean the right to left, left to right order. But if you put this order and now close around this order, then this means that, for instance, this one edge, you would also have it looping here, and you would also have a 1 going down here, yeah. And you would also have a 2 going down here. So you would have a path that goes 0, 1, 0, 1, 2, 0, 1, 2, 3. And this looks very bad because this does not satisfy the objective. So my point is, you could stop at this stage and think and say, okay, it's probably not positional. But also the proof tells you how do you construct a game which is difficult from an example of a graph which seems difficult to embed, such as this one. And this is how you should construct a counterexample. So start with your graph, give the power to the opponent, and then add a vertex, give it to Eve, and say that Eve can go everywhere. And we will see that a similar graph may be more complicated, but it's a similar gadget for the general proof. So it's not surprising that this is how you turn a graph to a counterexample. And this graph, well, if you think about it, Eve can win. How does she win? Well, whenever Adam, so Adam plays, right? And at any point, Adam can ask Eve to continue, right? And Eve would continue on the same place. And if we play like this, then the only number that can occur infinitely often is 0. So Eve has a winning strategy, which is always go back to wherever we were just before. Yeah. But she does not have a positional winning strategy, because let's say Eve always goes back to here, to the 1, then Adam can do 1 and then go back here, 1, 2, and then 1, 2, 3, 1, 2, 3, 4. So a positional strategy is not winning. Yeah. So this gives a counterexample to positionality. Is this clear?
Yes.
So in retrospect, it was not so complicated, but I think coming up with this counterexample is not so easy. I mean, it takes more than 10 minutes, or maybe you can get stuck for a few hours probably. Okay, so that's the last slide. So the slides are over, and now I'm happy to prove anything. So prove the theorem. I think the most sensible thing to do now is I can explain a proof of the theorem, just the positionality version. So let's go back to positionality version. So unless you have a, so I mean, are you interested or in seeing proof?
Maybe just in the direction from right to left. No, just to see how it works for the case, for a simple case of parity games or something like this. Yeah.
Okay. Okay. So let's do this. So here is where it gets technical. So I will stop the sharing.
But maybe you can just write on the board, no?
Yeah, that's what I'm gonna do. So here, do you have the whiteboard?
No, we see. Yeah. We
okay.
see something.
Good. So let me write again the theorem. So the theorem is that W is positional if and only if I hesitate. Okay, let's. So I'm gonna draw another version of the statement where I'm not talking about graphs defined over all ordinals. So I'm going to write the safe version. So for all kappa, there exists, so this is the real formal statement maybe. There exists a monotone well-founded. Now I will say kappa W universal graph. Now I should explain what this means. This means that the graph U satisfies the objective, yeah, as before. And second, that any graph G satisfying the objective, which is smaller than kappa, has a morphism into U. So for all such graph, if it's smaller than kappa, it has a morphism into U. Okay, this is just another statement. Okay?
Yeah.
And now we're discussing this direction.
From right to left. Yeah.
From right to left. Right? Okay. So, well, okay, so we want to show, we prove that, okay. So we start here, here's a game. That's my game G. Well, we want to prove that if I can win, then I can win with a positional strategy. So here's a winning strategy. Let's draw it kind of like a tree. It's not really important, it's just for drawing. So this is strategy S. So the strategy is a graph with a morphism towards G. Let's call this pi S. Okay. And now, so I want to show that I want to somehow fold this strategy. Yeah? This strategy is not positional in the sense that maybe here's a vertex V, it has several outgoing edges, and maybe in different occurrences in the strategy, well, we make different choices, and this is, I want to show that I can also have a strategy that makes always the same choice. Okay.
And
so
in pi S, also all paths belong to W, right?
Yes, I know exactly. I know that
Or
S
in S.
satisfies the objective. Yeah, it's a winning strategy. Yes, thanks. Okay, and now now I'm going to use my assumption. So I'm using my assumption for some. I'm choosing some cardinal kappa greater than the cardinality of the strategy, and I'm using my assumption. So I know that I have a well-structured universal graph. So let's make it big. So it looks like a line. So this is my graph U. So I know I'm just using the fact that there's an embedding like this. So this is my graph U. I know that U satisfies the objective, is well-founded, and monotone. Right? And now I want to use all of this to construct a positional strategy. And so I'm going to draw it here. So a positional strategy is a strategy which is a subgraph. So I'm just writing a kind of a copy of G. I'm going to call it P. And here it's going to be this inclusion, right, in the graph. So it's just for the sake of drawing something. And now I want to define here some edges in P. And the way I'm going to define these edges, so let's say that we have.
So we need to decide where to move in some vertex of a graph.
Yes.
So actually, there are many copies of this vertex when we can come
Exactly.
in our strategy. So if for example, for some strange reason, we make the same move all the time, then we can make this move, I guess.
Probably, yeah.
But so somehow you need to select one of the moves using this embedding, yeah.
Yes.
So how do you do this? Can
How
you
would
say?
you do it?
Yeah.
I'm sure you have it in mind.
So yeah, so you have
you probably
you have
say,
your strategy and you have many appearances of some node U. And then you
Yes,
have
so I have
this, yeah.
so I have many occurrences in my strategy, and maybe these occurrences they choose different moves, but I need to choose one move which seems to be the best.
so you take the minimal ordinal
Yes.
and
So exactly. So maybe there's infinitely many occurrences. I look at the image in my well-founded graph, and this has a minimal element, right? This
yeah.
thing. And this thing corresponds to something, and then I follow this. Okay, and then you
Yeah.
need to check that it works, but that's the proof. So I should let me maybe finish the proof. So actually I'm going to do this just for the sake of clarity of the proof. I'm going to do this not only for vertices that belong to Eve. I'm going to do this for all the vertices. So I'm going to define here a phi prime. And phi prime, let me write here the definition. Phi prime of V is the mean.
No, but for other vertices, we cannot restrict. There should be all edges, no?
Yeah, but I'm just defining now a map from the game graph or the vertices of the game
Okay.
to you, yeah? So it's the mean of phi of pi s minus 1 of v, right? So if v is this green guy here, this is pi minus 1, it's the occurrences in the strategy. Then I'm looking at the image and taking the mean. Okay, this defines psi prime, and then for the positional strategy, I put here in P all the edges that are coming out of pre-images of phi prime. Yeah, is this clear? I hope I don't have to write it down. And then the claim is that psi prime is a morphism. And this is what we should check. Yeah, that's my claim. And why is this good? Because, well, now I have my strategy, and I should show I have defined a positional strategy. I need to prove that it's winning, but I know that that U satisfies the objective. Yeah. So if I can prove that psi prime, phi prime, sorry, is a morphism, then any path in there maps to a path actually in U, and all the paths in U satisfy the objective. So I'm done, right?
So let me try to say it again. So
Yes.
you have some strategy, and we assume we draw it as a tree, right? Basically. Well, in the most general case, we can assume that this is a tree. So just a tree
The
of all
strategy
paths that
S,
are
you're talking
yes,
about S?
strategy
Yeah.
S, and there are some, and this is just a tree of all
Yeah.
paths that are consistent with it.
Yeah. I mean, we don't require it neither in the definition or in the proof, but if it helps your thinking, you can think of it as.
And then, so when I'm in some node, and now, and there are like green points, in this tree, and these are like different ways I can come to this node according to my strategy.
Yes, exactly.
And they are all mapped. And okay, yeah. But if I'm using a positional strategy, I don't know which way I came here. But then all my paths that are consistent with Fs are somehow ranked by this universal well-founded graph. And I'm kind of saying that I'm choosing. So, and like the less is the mapping, the less is the value in this well-founded graph,
Yes.
the worse is the situation,
The best,
as I
actually.
understand. So
the best is the situation. It's a kind of best future proof. So think of, like, for instance, what we had for Kobushi.
but let's say I think like it's the hardest situation. I mean, and then I'm choosing. So and I'm saying, okay, I have some finite paths that I can come to be, and then I'm choosing. So I will do something as which has the lowest rank, like in this
So do you
graph.
want to
Yeah,
say
I
at some
think it's
moment
more.
that you will actually follow, since the ranks are well founded, you will from some point you will follow one strategy, and so this should be winning, or
No, that's not true.
not
There's
true?
jumps. It's not the case that.
Well, I think well-foundedness is used to show that I can choose among all finite paths that I can come, one with the minimal rank.
Yes.
By rank, I mean just um,
The image by phi.
the image in the universal graph. Okay, and then this defines me a positional strategy. Then we have to somehow show that it's winning.
Yes.
And then I don't know, there should be some invariant or something that ensures that if I play with this against this strategy, then something good happens.
Yes.
Right?
Yeah. And what happens is that if you look at a path in your strategy, what I claim is that it maps to a path in the universal graph, because each edge maps to an edge in the universal graph. But the paths in the universal graph all satisfy the objective.
Yeah, but then you're showing that it can be mapped to a universal graph just by induction, right?
No, it's just I'm proving that phi is a morphism. This means I will prove that any edge that appears, it's a simple argument now to show that it's a morphism. You just need to prove that an edge appearing here actually appears here. And this will use the monotonicity. Yeah, this is, maybe you've overlooked that we have this assumption. We've not used it so far. And this is what we now use. Yeah, so I can argue. Yeah, should I prove this? So now,
yeah,
there just remains to prove that phi prime is a morphism. Okay. So let's take an edge here, and I want to show that it appears. So I have an edge, and my edge was selected in my strategy, which means that, okay, let's say it goes to a blue vertex, V prime. And the fact that it's selected in my strategy means that there is this minimal occurrence here of V, whoops, green. And then this picks a yellow edge, and this edge goes to one occurrence of the blue guy, that appears in the game, and this is the yellow edge, right? But this blue guy is there's many other blue guys, right?
Mhm.
I hope I'm being clear. And now all these blue guys, well, they appear somewhere in the graph. I don't know, maybe like this. And there's a minimum, and this is phi prime, but this guy certainly does not correspond to the minimum, but goes somewhere beyond the minimum. This is phi. And what I know is that phi is a morphism. So phi being a morphism tells me that there is this edge here.
Mhm.
And now, since my graph is monotone, this tells me that there is also this edge here. And this is what I wanted to prove.
That's because of the monotonicity property, because this blue guy is less than that blue guy.
That's
Right?
just one side of the monotonicity property, right?
Yeah.
Yep. Yes, so we're just using one. I can discuss why I still require two, but it's a bit... yeah, you don't actually need the two. But it makes more sense to have the two, because also you can get the two in the other side of the proof. It's also that here I put something under the rug that in this proof, and also in the definition in all the definitions that I've seen so far, I'm implicitly assuming that the objective is prefix independent, and that we don't really care about the starting vertex. Because when I say that a graph satisfies an objective, I mean all the paths and not all the paths from the starting vertex. But if you want to look at non-prefix independent objectives, then you need to adjust a bit the definition of being universal and of satisfying an objective, but it all ends up working, but you need some adjustments. And when you do these adjustments, then when you do the proof, you actually use the other side in monotonicity, which is why I just assume that it's there in general. But yeah, that's a good point. We're just using one half of the monotonicity requirement here. So the other half of the monotonicity requirement is somehow hidden in the fact that here we assume that the graph satisfies the objective. If you define universality for objectives that are not prefix independent, you need to also talk about parts of the graph that do not satisfy the objective. And then in the end of the proof here, you need to say that your strategy maps any winning vertex to a part of the graph which satisfies the objective. And for this, you're going to use the other side of monotonicity. So in this case, it's not used, and you don't have to assume it, but it's used for the more general statement that does not assume prefix independence. I mean, it's a subtlety. It's not. In any case, yeah. But it's a good point. But the answer is a bit subtle, not so interesting.
Pierre, sorry, maybe just a question before we finish. So about algorithmic things. So what's the claim? If I have a universal graph for a finite graph, and let's say for graphs of size at most n, right? And then I can solve the decision problem in time which is proportional to the size of the graph.
Yeah.
Then just for any object.
Yes.
or not?
Just what was the last two words?
For any objective.
Well, for the objective that I'm universal for, right? But yeah.
Yeah, for the, I see. Well, assuming that I have some, what I should assume about the objective. So like it's should be constructive in some sense, or
So you should assume that the objective is positional. But this also works for finite memory with the adequate algorithm. But let's say positional, and you have a universal graph, then you get an algorithm. But this has been known for a few years. I mean, it's not as new as this thing. But yeah, it's so the value iteration algorithm is just do what you would expect. Like you're trying to find an embedding. Let's say now we do it for a game. Okay, so you're looking for a map from the game to the graph, such that well, for Adam vertices, all the outgoing edges are preserved, and for Eve vertices, one outgoing edge is preserved at least. And then this map, then if you look at exactly these edges that are preserved, if you can find such a map, it gives you a strategy. And conversely, if you have a strategy, then since the graph is universal, there exists such a map. So it's a direct argument. There's nothing complicated. And now the value iteration algorithm, what it does is, so you know that the game is winning if and only if there exists such a map. And it's easy to see that there is a minimal such map. Because if you take just the pointwise mean of two such maps, then it's such a map. So what some people would call a valid progress measure. Yeah, so then the algorithm just looks for a valid progress measure in a greedy fashion. And since you have this fact that the minimum of two valid progress measure is a valid progress measure, you will never exceed the minimal fixed point, right? The minimal valid progress measure. So it's a valid algorithm.
it's like you're finding a fixed point, right?
Yeah.
And you just start with an arbitrary, with the first mapping, then apply the function until you find a fixed point.
Yes.
Okay.
But you can understand, I think it's nice to see everything as a kind of a graph morphism. I mean, it's the point is there's in these progress measure algorithms, people talk about valid and invalid edges, and then they say that the vertex is valid if for an opponent vertex it needs that all the outgoing edges are valid, and for if vertex needs to have one valid outgoing edges. But being valid just means that the edge appears in the image, right? So you have a mapping, this is what people call progress measure, and then validity means appearing in the image. And you look for a valid progress measure, which, yeah, blah, blah, blah. I don't know if there's, is this clear, what I'm saying, Sasha? I mean, at least for you, maybe?
Well, I don't understand what in terms of ages, what is the step? So what is the update?
So the update
You
is
have some age that doesn't have a representative in a universal graph, and then
yes.
what you're
So
doing.
at any point in the algorithm, you have a map from the game graph to the universal graph, right? And what you want in the end is that each Adam vertex and each outgoing edge is valid, and for each Eve vertex there is a valid outgoing edge. Yeah.
Yeah.
And valid means that the morphism preserves the edge. So if you look at V and V prime, you look at their image, then you look if the edge is here or not, and this is valid or not. So for a graph, it means a graph morphism. I mean, if the game is controlled just by the opponent, this means that all the edges have to appear in the image. But for a game, it's a bit relaxed, because for vertices that belong to Eve, you just need one valid outgoing edge, right? And now the update is, well, take a vertex which is not valid. So For an if vertex, it means there is no edge, no outgoing edge in the image, and for an Adam vertex, it means there is one outgoing edge which is not here in the image. So take such an invalid vertex and move it a bit in your mapping until it becomes valid. Or just move it one step. This would give also the same complexity. Just move it one step in the image. That's like a binary update. And this is the algorithm. And at the end, the algorithm, when the algorithm stops, then you are guaranteed that everything is valid, which means you have found such a map. And if the game is, if there is a winning strategy, there has to be such a map, and you've actually found the minimal one. And conversely, if the game is losing, there cannot be such a map. So this is why the algorithm is correct. So it's
Yeah, and somehow we should also argue that you cannot surpass the minimal
yes,
valid mapping.
yes, and this is a direct consequence of monotonicity again. That the mean of two of two valid maps is a valid map. I mean, it requires some proof, but it's a direct check, and it follows from monotonicity.
Yeah, okay, but still, really, it's so difficult for me to follow this. But I just have some general question. So somehow, imagine you have proved that for example, for parity games, you have this graph, universal graph, and so you prove that these games are positional. But then we want to show that for one of the players there exists a positional strategy. So in this way we rely on the Martin theorem on Borel games, or we can get something directly from this argument.
No, you don't get determinacy from this.
So this technique is not doesn't allow us to prove the positional game are determined.
It's not true in general.
The positional game, parity games, are determined without going through Martin theory. But if you believe that they are determined, you prove that there exists a positional strategy.
Exactly. I mean, you can talk about positional strategies independently of being determined or not. And you can.
Yeah. I understand this, but somehow strange still that for.
Yeah. So the answer to this is that really we are in a scenario which is super asymmetric. We don't care about the opponent. It's like the opponent does not even try to derive strategies or anything. He's just
No, I understand, but this
dummy.
is somehow strange because it could be that somehow you explain when you have a strategy, when the opponent have strategy, and then you prove that if for a countable so what is good here, because usually when we can prove something for how it's natural to prove the determinacy for Borel games. You prove that if it's true for some family of sets, this family is closed under countable intersection. But if you just prove it for, usually you cannot prove it. So if you have an intersection, it's not clear. You don't have the same. One of them can be determined, and the other determined for other players. So it's not clear, and it seems that maybe you can prove that if there exists something for every some classification graph for every condition W, then there exists some classification graph for intersection of all conditions. And in this way, maybe you can prove Martin theorem in a new way, or just maybe not in a new way, but understand the proof, old proof in a new way, or something like this. No?
I'm not sure what you mean.
No, I don't mean anything specific, but just maybe you can somehow prove So what is the problem for Borel games? So if you have this, you cannot prove that the class of properties for which the game is determined is closed under countable intersection, because you have just many properties. For some of them is determined in one direction and for some in the other direction, and for intersection we don't have anything. If the parts are different, or and but maybe if you prove that the winning strategy is equivalent to existence of something, maybe you can just understand what is determinacy in these terms and prove that it's closed under countable intersection.
I see your point that since we're completely asymmetric, we kind of gain something that the question of determinacy doesn't really have. I guess this is what you mean. And so
No, I can maybe your picture can be somehow symmetrized and provide as a
the thing is that here, I mean, if you care about objectives which are, let's say, positional for both players, then these are not really interesting, because we know
no, we don't need positionality. So if you allow memory, it means that you allow some graph of non-trivial width.
Yes.
Okay, just forget about any restriction on width. Maybe there is something which is still you can this embedding can have, because in this Borel theorem there is also a very strange thing which is called this mapping. They for every game they construct something which is a kind of very large game which is mapped to another game in some way, and something like this. And
yeah, I was planning to actually understand this proof better, but I haven't got time to get
okay.
So far.
Yeah.
So I wouldn't know what you're
No, it's a part of the mystery of all this, but okay.
Yeah, but yeah, I mean, definitely I want to understand some relations with Borel determinacy theorem, but it's not at all clear.
Yeah.
If yeah. So there's also one other question that stems from this, is let's say that you have an assumption on your, let's say that, for instance, you're looking at a Borel objective, and let's say that it's let's say that also you have let's say you're looking at finite alphabet, okay, or countable maybe, but you have a bound on the alphabet, and can you have something like, if my objective is positional on all graphs of cardinal kappa, then it's actually positional on all graphs. And this is related to this because it would mean that you don't really have to have this. It's sufficient to have a bound here on kappa. You don't need to do really all kappa, but under some reasonable assumptions, then you can just look up to such cardinal. And this I don't know if it's true or not, and I don't really know how to attack it. I think it's also one interesting next step, and it could be that that understanding better. I mean, for now I have absolutely no understanding of Martin's proof because I didn't have time, but it could be that this is the good direction to look at. I don't know.